Hello everybody! So today we're going to be talking about another way to find volumes using an integral. And in the past we've already talked about using slices of a figure and adding up all of their areas to get a volume. Now we're going to talk about getting volumes by revolution. Now when we say revolution, we mean revolving or spinning a shape. So sometimes we can find the volume of a three-dimensional shape by taking a curve, like this area underneath R here, and rotating it around a given axis. Now the axis could be any line on the graph. It doesn't have to be just the X and Y axis. It could be any vertical or any horizontal line. When we do this, when we spin a shape around a line, each of the slices, going back to what we were already talking about with slices, is going to be a circle. To compute the volume of a three-dimensional figure that we create when we do this process, when we revolve around a given axis of rotation, we set up an integral that looks like this. We do an integral from A to B, and it could be in terms of X or in terms of Y, you just use your bounds. But because it's always going to have circle slices, we're going to use the formula pi r squared inside of our integral because each of these slices will be circles. And then we're going to need to make r be in terms of X. Or Y. And then we would put a dx or a dy depending on what we were integrating with respect to. Now, sometimes when we do this revolution, we end up revolving a figure that isn't directly connected to the axis around which we are revolving. So it creates a shape that has a hole in the middle. If you look at this three-dimensional model here, you can see there's a tunnel through the middle of this shape. Anytime there's that gap between the axis around which you are revolving, so there's a gap between the axis that you're revolving around and the function that you're revolving, you're going to know you actually are going to need to remove the hole in the middle of the figure. So to do this, we set up two integrals. We would do the integral from A to B. We would still use pi r squared because that's our area formula every single time when the shapes are circles. But this would be what we call big R. And then either dx or dy minus the integral from A to B of pi times what we call little r squared, and then either a dx or a dy depending on which direction you're revolving. Now, what do this big R and this little r stand for? The big R stands for the outer radius in terms of X or Y. And the little r stands for the inner radius in terms of X or Y. So in this picture, if we wanted to label our big R and our little r, big R would be the outer function minus the axis. That would be big R. And little r would be the inner function minus the axis. So if we were doing top minus bottom, we would do outer minus axis, inner minus axis for the big R and the little r. Think about this as removing the hole that's in the middle. So you want the volume of this entire shape with no hole, so going all the way to the outer edge, and then you want to take out the volume of the hole that's in the middle. And we set this up as two different integrals every time. So let's take a look at number 1. Find the volume of a solid of revolution generated when y equals negative x squared plus 4 and the x-axis is revolved around the x-axis. Show your setup and then use your calculator to evaluate the integral. So we are revolving the area that is trapped between this function and the x-axis, but between negative 1 and 1. So the area that we are really revolving would just be this area here. Now we're going to revolve that around the x-axis. So I usually draw a little circle to show what I'm spinning around. I'm spinning around the x-axis this time. Now a great next step is going to be to draw in the three-dimensional figure. So to do that, we're going to reflect this area around our axis so we can see basically the bottom half of the shape. So if I do that, it's going to look like this. And then you can actually draw in, if you draw in ovals on the two ends, it helps you visualize that this is actually a three-dimensional shape that's spinning. So now the question is, how do we actually get this volume? Well, as soon as I see that I'm spinning, I know that my area formula is going to be pi r squared. That's step 1. Step 2 is going to be to figure out what r is in this problem. So in this problem, because I'm spinning around the x-axis, I'm going to set this up in terms of x. Just like when I'm perpendicular to the x-axis, I set this up in terms of x. To get the radius of one of these circles, I'm going to do the top minus the bottom edge. Now the top edge is this function, negative x squared plus 4, minus the bottom edge of the radius is the line where x or y is 0. So if I simplify that, I would do x squared plus 4, and I wouldn't worry about the 0 because when I subtract 0, it doesn't change anything. Now I'm going to go ahead and set up an integral. So I'm going to integrate from the beginning x value, which is negative 1, to the ending x value, which is positive 1. And then I'm going to set it up with pi something squared dx. Now that something is going to have to be my radius, and I just figured out that my radius is negative x squared plus 4. Now this problem specifically says that, hey, once you have it set up, just go ahead and type it in. So I'm going to type in from negative 1 to 1 of pi parentheses negative x squared plus 4 parentheses squared dx, and I'm going to get 85.032 for my volume of my shape. Okay, let's take a look at the next problem. So problem number 2 says find the volume of the solid of revolution generated when x equals negative y squared plus 1 and the y-axis between y equals 0 and y equals 1 is rotated around the y-axis. So I'm looking for the area trapped between this graph and the y-axis between negative 1 and 1. So I'm taking this area and I'm spinning it around the y-axis this time. So I'm drawing in that little circle to show what I'm rotating around. Now if I sketch in the other half of my shape, it's going to look like this. So I'm going to get this solid, this three-dimensional figure that looks kind of like, almost like a football. Now, because I'm spinning something, my area formula for each of my slices is pi r squared. And because I need to figure out this in terms of x or in terms of y, I'm going to set this up and I'm going to try to figure out what my r represents. Now in this problem, because I'm spinning around the y-axis, I'm going to set everything up with respect to y. So I would do, instead of top minus bottom, I would do right minus left to get the radius. Now the right edge of this slice would be on the function negative y squared plus 1 minus the left edge would be on 0. So I would have negative y squared plus 1 is my radius. Now the third step would be to set up the integral. So I would have the integral from the lower y value, which is negative 1, to the higher y value, which is positive 1, and then pi times the r squared dy. And in this problem, the r would be negative y squared plus 1. Now this problem says no calculator. So how would you do this without a calculator? Well, the first thing that I would do is I would try to rewrite this integral in a friendlier way. So I would have the pi pulled out because I'm going to multiply by pi at the end after I evaluate my integral. And then I would multiply this out. So I'm going to be doing negative y squared plus 1 times negative y squared plus 1 dy. Now when I do that, I get the integral from negative 1 to 1, pi's on the outside, and inside of there I have y to the fourth minus 2y squared plus 1 dy. I'm just foiling those together, multiplying them out. Now I'm going to do my antiderivative. Now the antiderivative of y to the fourth would be 1/5 y to the fifth. The antiderivative of 2y squared would be minus 2/3 y cubed. The antiderivative of 1 would just be plus y. Then we have our plus c evaluated between negative 1 and 1. Now my next step would be to plug in my numbers. So when I plug in the number 1, I get 1/5 minus 2/3 plus 1 plus c minus, then I'm going to have negative 1/5 because negative 1 to the fifth power is negative, plus 2/3 minus 1 plus c. Now the plus c's are going to cancel. If I distribute the negative, I get pi times 1/5 plus 2/3 plus 1 plus 1/5 minus 2/3 plus 1. Now the plus 2/3 and the minus 2/3 cancel. So 1/5 plus 1/5 would be 2/5 plus 1 is 2/5 plus 2. So I would get 2/5 plus 2 all being multiplied by pi. Now 2 is really 10 over 5. So I would end up with 12/5 times pi as my final answer. Now on the AP test, this is kind of a mixed question. About 50% of the time you're going to have a calculator and about 50% of the time you're not. So it's going to be really important that you practice working some of these out without a calculator, especially because it also helps us review our antiderivative skills and our arithmetic skills. Let's take a look at problem 3. So if the region enclosed by the y-axis, the line y equals 2, and the curve y equals the square root of x is revolved around the y-axis, find the volume of the solid when generated. Now this one doesn't have a picture, so I'm going to go ahead and just sketch a picture. It doesn't have to be a great picture. It just has to give us a visual of what we're doing. So the line y equals 2 is a horizontal line up here. The curve y equals the square root of x looks like this. And I'm also using the y-axis as a boundary. So if I'm using the y-axis, the line y equals 2, and the square root of x line as boundaries, then the area that I'm rotating is this area here. Now it says we want to rotate around the y-axis, so we're going to be doing everything with respect to y in this problem, which means that right away I'm going to leave this a 2, but right away I'm going to rearrange this equation and get x by itself. So if I get x by itself, this becomes x equals y squared. I'm just going to label that there. Another thing I'm going to be very curious about is where these intersect. Now if y is 2 and x is y squared, then this ordered pair is going to be 4, 2 on the graph. Now the reflected region would be over here. So you can kind of imagine if you rotated this, it would look kind of like a cone. So my steps are, first, write down my area formula. Because I'm rotating, all of my slices are going to be circles. Second, figure out what your radius is. So in this problem, because I'm rotating around the y-axis, my radius is going to go from right to left. So I'm going to do y squared minus 0, which is just y squared. Then set up your integral. So I'm going to have the integral from 0 to 2 of pi times my radius squared dy, because everything's in terms of y in this problem, and my radius is y squared. Now, this one also says no calculator, so we're going to have to kind of work this out. You're always going to want to pull out the pi. It just makes your computations a little bit easier, since pi is not a nice number to work with if you don't have a calculator. Times the integral from 0 to 2, and then I'm going to simplify this. Y squared squared is actually y to the 4th, dy. Now I'm going to need to do an antiderivative. So I'm going to have pi times, the antiderivative of y to the 4th is 1/5 y to the 5th plus c evaluated between 0 and 2. Now if I plug in my numbers, I'm going to have pi times, if I plug in 2, I'm going to have 2 to the 5th, which is 32 over 5 plus c. Minus, if I plug in 0, I'm just going to have c. So the c's cancel, and I end up with 32 pi over 5. Now for problem 4, it says find the volume of the solid of revolution formed by rotating the finite region bounded by the graphs of y equals the square root of x minus 1 and x minus 1 squared around the x-axis. When it says the finite region bounded by the graphs, it literally means trapped between. And we're revolving around the x-axis, so we're going to do everything in this problem with respect to x, which means it makes sense that these equations would be written with y by themselves. So we're going to be revolving this region around the x-axis. So the reflection of that region would look like this. Now, as soon as I draw that, I see that this is one of those problems that has a hole in the middle. There's a big gap between the line that we're revolving around and the actual function's edge. So there's a gap there, which means this time we're going to have to take out the hole, the missing chunk in the middle. Now, first, our area formula is still pi r squared. But this time, instead of just needing a little r, we're going to need a big R and a little r so that we can subtract the inner edge. Now, big R is going to be the distance between the outer edge and the axis. So if I do top minus bottom, this graph right here is the square root graph. So I would have the square root of x minus 1 minus, in this case, the bottom is 0. So just the square root of x minus 1. The inner radius here, that little purple line that I drew, is going to go from the squared graph to the 0. So I would have x minus 1 squared minus 0, which would just be x minus 1 squared. Now when I set this up, I'm going to have two separate integrals, and it's very important that you make this two separate integrals. So I'm going to have the integral, and it looks like from 1 to 2 of pi times big R, which is the square root of x minus 1, squared dx, minus the integral from 1 to 2 of pi times the little r, the inner radius, dx. Now this problem we're just going to go ahead and do on our calculator. So once we have this set up, we're just going to go ahead and type this in. Math 9, integral from 1 to 2 of pi parentheses square root of x minus 1 squared dx minus math 9, integral from 1 to 2 of pi times x minus 1 squared dx. Now sometimes it takes a minute to compute these, but this one seems to have gone pretty fast, and I have 0.942 would be my volume. Okay, last couple examples, and then we're going to practice this a lot of times when we see you in class tomorrow. So it says, find the volume of the solid generated by revolving the region bounded by the square root of x and the lines y equals 2 and x equals 0, and rotating it around. Now the first thing we're going to rotate it around is the line y equals 2. Now y equals 2 is a horizontal line. And horizontal lines act like the x-axis. So with this problem, we're going to set everything up with respect to x. So we're going to sketch a little picture. It doesn't have to be great. It just has to kind of help us visualize what's going on. So if I sketch a little picture here, I'm revolving the region bounded by the square root of x, which is this, the line y equals 2, which is this, and x equals 0, which is this. So it's this same region, which we kind of looked at before. And in this problem, I'm going to revolve it around the line y equals negative 2. Now, when I do that, the reflection of this region is going to be way down here. Because there's this huge gap between the line and where the graph starts, so there's going to be a huge gap between the line and where the graph starts when we reflect it. Now clearly in this problem there is a giant gaping hole in the middle of the problem. I would imagine like if you turn this like this, it would be kind of like the Colosseum. There's huge like seating on the sides and then a flat spot in the middle. So it's going to be a huge like Colosseum type structure when you actually do the spinning here. So step 1 is going to be that our area formula, because we're spinning, are always circles, so pi r squared. Step 2 would be we need a big R and we need a little r this time because there's a big gap in the middle. Now the big R is going to be from the outer edge to the line around which you are revolving. So that radius would be 2 minus this line is negative 2, top minus bottom, so 4. Little r would be the inner edge to the radius around which you are revolving. So little r would be the square root of x minus negative 2, which would be the square root of x plus 2. Now my third step is going to be to set up two different integrals. So I'm going to integrate from, now where do these start? 0. And then where do these intersect? Well, the graph of y equals the square root of x and the line y equals 2 are going to intersect at the point 4, 2. So from 0 to 4, and then I'm going to have pi times big R, which is 4 squared, dx minus the integral from 0 to 4, and then pi times little r, which is the square root of x plus 2, squared dx. Now once again, I'm just going to type this in on my calculator. So I'm going to go to math 9, integral from 0 to 4 of pi times 4 squared is just 16, so I'm just going to put a 16 there, minus math 9, integral from 0 to 4 of pi times the square root of x plus 2 squared dx, which is 58.643. Now in the next part of this example, we're going to take that same region. So I'm just going to go ahead and re-sketch it here. So it's this region bounded by these graphs. only this time I'm going to revolve it around the line x equals 4. Now x equals 4 happens to be where these graphs intersect. So I'm going to be revolving it around this line right here. Now the reflection then would look like this. And once again, there's a big gaping hole in the middle. There's a big empty spot. So I'm still going to need two integrals to set this up. But because this is a vertical line, I'm going to need to set everything up with respect to y. So our area formula is going to be pi r squared. We're going to need a big radius and a little radius. Now, in terms of y, this is still the graph of y equals 2. And this guy right here, if we rearrange the equation y equals the square root of x, would be x equals y squared. So that big radius would be the outer edge connecting to the axis. Now, when I do right minus left here, the axis is the right. So I would have 4 minus 0, which is 4. Little r would be the right minus left, but to the inner edge. So I would have 4 minus y squared as little r. My third step would be to set up two different integrals. Now, in terms of y here, I'm going from 0 to 2. So from 0 to 2, pi times big R, which is 4, squared dy, minus the integral from 0 to 2 of pi times little r, squared dy. And then I would just type this in on my calculator. Integral from 0 to 2. Now 4 squared is just 16, so 16 pi minus math 9, integral from 0 to 2 of pi times 4 minus x squared, squared dx. Now I know we did this in terms of y, but remember on your calculator it's just an arbitrary variable, so you can just type in x. It would be 46.914 as our volume. Okay, thank you guys so much for watching. I know this is a longer video, but now we're just going to give you a bunch of days in class to practice this. So have a great night, and I will see you tomorrow.